Hello, YouTube. Hello, Zoom. Hello, Room. We're going to do some stuff today about the concept of degree. But before we get there, I just want to finish off what we were up to last time. So let me just make this slightly bigger. Right. So last time I wanted to replace two of the terms in Clemens's diff operator with one defined using shift. So this makes it look almost like the infinitesimal derivative you may have learned in high school, except that one of the formulae that isn't being diffed is being shifted. And that gives you, if you remember our diagram with the rectangle in the corner that was extra, that's just being folded in. But I didn't manage to finish the proof that this really does give you forward difference. So I'd just like to do that now. So here we go. I've got the most of the proof already set up in here. I just need to do the multiplication case again. So I'm going to say test and hope that network is good enough. Right. So what happened here? Annoyingly, we'll see ask keeps expanding, shift R. So we got we've got this business. Right. So what I'm going to do is I've got two induction hypotheses. What do they tell me? So let's just write down a collection of things we know. What did I just do? Let's write down a collection of handy things we know in a comment. Right. So we know, because Q and R are smaller than P, we know some facts about evaluating Q, and we know some facts about evaluating R. But there's something else that we know about evaluation and shift, if I can only find it. We know this fact. And in particular, we know that this is true for R. So right. So these are three useful pieces of information. And I can see, in particular, the third of these equations tells me that I can do something. I can turn that thing into a shift if I want to. I've got two ways I can do something with evaluating R at successor of n. And I need somehow to get shift involved. There's a shift on the right-hand side of the equation. There's no shift on the left-hand side of the equation. So I'm going to use, at some point, I'm going to use this third fact to make a shift appear. Okay. But my first move is simply going to be to swap out evaluate Q of successor of n for what I know it's equal to inductively, because that I'm entitled to. So what do I do? I say by root, I write set parentheses, I pick up the entire left-hand side of the equation and I paste it into the parentheses. Then I pick up the right-hand side of the induction hypothesis. I hit copy. I select this thing, which is the left-hand side of the induction hypothesis, and I hit paste. And then I realize I need an extra set of parentheses around that because Bob maths. Okay, everyone see what I did there? And why it's a good move. It's a good move because it gets rid of things that don't... We're stepping from the left-hand side of the equation and we're introducing some of the ingredients of the things that show up on the right-hand side of the equation. So we're heading in the right direction. Let's hit send. And accept. And we get two sub-goals, one of which is just to justify the step we took. And the other is the rest of the proof, really. So this one, conceptually, all we're saying is that we need to justify the step we took, to dig out the place where we used the induction hypothesis, and we do that with under. Okay, so that's kind of conceptually part of the same move. It often happens that if you use an equation to modify one side, if you rewrite by an equation deeply inside an expression as a by root move, you will need to justify taking that step using under to dig out the place where you made a change. So that's all that just happened. So this under times kind of goes with that by root. But now we're left with the rest of our problem, and I'm going to manually put the shift back. Ask likes to expand that definition over and over again, whereas I want to see what it used to be. Okay. So, any suggestions for what to do next? Do you see anything that you can do to get the left-hand side a little bit closer to the right-hand side? We were playing the game where we're just trying to the game is now to use algebra in order to decrease the distance between the left-hand side and the right-hand side, just by making moves that we're allowed to do. So can you see how we could get our hands... so this is one of the things we want on the right-hand side, evaluate Qn times evaluate Rn. Can you see how we can get our hands on that on the left-hand side? How can we make that appear? Any suggestions? Sorry? No, we're not really there yet, because we've got a times on the left and we've got a plus on the right, so we can't go under anything. But yeah, can you see anything you can do to get your hands on a copy of this? I mean, I'm not asking you to do anything that you didn't learn to do at school. We're entitled, when we see this thing, to multiply it out. Yeah? And that will get us... So we've got evaluate Qn is one of the things inside this sum that is all being multiplied by evaluate R at successor of n. And, we can now multiply that out. So it's another by root. And then I'm going to pick up the left-hand side of the equation, paste it in the parentheses, and then I'm going to cut that, paste it twice. And then I have to count brackets carefully, otherwise it'll all go horribly wrong. I think that's it. You know you've become a computer scientist when your subconscious counts brackets for you. It'll happen to you eventually, and then you'll think, what has been done to me? That is once again Shift R. Okay, so let's see where we are now. We've multiplied out this bracket. We got one sub-goal because it was the move we made was directly justified by a distributive law that we proved ages ago. So let's see. So this is pretty good. We've got two terms on the left. We've got three terms on the right. And now we're seeing that we've got diff q multiplied by evaluate r at the successor of n on the left-hand side. And we've got diff q multiplied by evaluate shift r at n on the right-hand side. But looky here, we know those are equal. So we now have two copies of evaluate r at successor of n, and we can do two different things to them. So I'm going to propose that we turn this copy into evaluating shift r, and we use the induction hypothesis for this copy, and that will get us some more things we like. So again, next step is another by root. And what does that do for us? I'm going to take that thing there, copy it, paste it. And then I said the one that is multiplying the diff, I'm going to get by evaluating shift. I put that there. And then for this one, I'm going to put this induction hypothesis there. Sand. Okay. So now I got two sub-goals. The first sub-goal is to justify what I just did. And that's going to be a load of under with annoying shift again. Right, I'll tidy this up. Right, so that's under plus. And then what do I get? And then this, you can see what we're up to. This is under times. And so is this. It's a bit messy. I'll tidy it up when I post the update. Okay, so we've made that move. And now, again, ask keeps expanding shift, and I keep not wanting it to. We're nearly there. So we're still working to make the left-hand side closer to the right-hand side. Let me just pull up. We've almost made it. You can see that we've got one of the terms we like. And if we multiply this out, we'll get the other two. So let's just do that. So again, I'm going to pick up the whole left-hand side of the goal, paste it into my root, and then massage. And I'm going to hit send. And this time I only get one sub-goal because we actually made it all the way to the right-hand side. We just have to do some unders to justify the step we took. So hit send on under plus. And then what have we left? I wish I could see what I was doing. Actually, that did it. We're done. That's the thing with Ask. You're always finished one step before you think you are. It's annoyingly clever. So yes, that's the shift version of diff sorted out. Where did I put it? I put it here. Maybe I will just make it a little bit cleaner. So it's very similar to the derivative you learned in high school, except that because we're dealing with a difference, a step size of 1 rather than an infinitesimal step size, this shift is saying we need to make R take a step. And by the way, you would get the same answer if you did the shift to Q instead of R. You have to shift one of them and not shift the other, and it doesn't matter which one you pick. So that's the story of this particular difference operator. But the real point of this lecture is to investigate the notion of degree. A degree of a formula is a kind of measure of how weird it is. You know, you might have heard words like constant and linear and quadratic and cubic. These are adjectives which are talking about degree, namely degree 0, degree 1, degree 2, degree 3. The degree is kind of the highest power of the variable that shows up when you multiply out the formula. In particular, it tells you to some extent, well, to a considerable extent, how many rows of differences you need to compute the sequence that the formula generates. So do you remember when we built the triangle numbers, we started with 0, 1, 1. 3 rows in the difference table, and that generated the triangle numbers. The triangle numbers are quadratic. But when we wanted to build the cubes, it took us 4 rows of differences. So if we're looking for the recipe for how to set up the difference engine to output the sequence generated by a formula, then the degree is what tells us how many rows we need to kick off with. Okay, there's an added extra thing going on in terms of how to manage constants. Think about this for a moment. Suppose you know a formula has a degree of something or other, you know, a degree of n. What's the degree of the formula if you multiply the formula you first thought of by a constant? You know the degree of x squared is 2. What's the degree of 3x squared? It's still 2. So if you multiply a formula by a constant, that preserves its degree, unless it's one very, very special constant. Which constant can you multiply x squared by to get something that's not quadratic? 0, right? Multiplying by 0 just nukes everything. So we better be careful about the degree of 0. Also, if you think about it this way, if you're trying to set up a difference engine to compute the sequence that is always 0, how many rows of differences do you need? I mean, if you think about it, none at all, because adding starts from 0. So no difference required. Whereas for any other constant than 0, you need at least one row of differences to say what the constant is. So we're going to treat positive constants and 0 slightly differently here. And that's going to turn out to be crucial for your homework. Okay, so I've got myself a box. So that's the point. That's one reason why we need to have a minus infinity knocking around, because that's going to be the degree of 0. 0 is so dangerously non-growing that we give it degree minus infinity. Okay, so I'm going to work inductively on the formula. And then I have to look at the formula. Right. So if the formula is a variable, is the variable, then that's going to be degree 1. Right? That's with it. X is most definitely linear in X. Okay, but as far as the numerical constants are concerned, I'm going to have to look at the constant to see whether it's 0 or not. I'm also going to change these terrible names to Q and R. Okay, so we said that the degree of a positive constant is going to be the number 0, but the degree of 0 is going to be bottom, negative infinity. Right. Okay, so now if we want to compute, if we're building up a formula by adding 2 smaller formulae, we are entitled to know the degrees of each of those 2 smaller formulae. How do we figure out the degree of Q plus R? Like, what do you get if you know that one formula is linear and another is quadratic? What do you get if you add them together? Also, you should consider last week's homework to be that is, of course, the joy of having family who don't remember that I work for a living. No, I do not wish to talk to my brother while I'm giving a lecture. Yes. Anyway, although this lecture is going to underrun, so maybe I should have taken the call. But anyhow, so last week for your homework, you manufactured some gadgets relating to botnums, and I was very carefully trying to line you up with the right tools to do this particular job. So what do you think we should use to compute the degree of a sum? Did I hear somebody mutter B max? Right? So if you're adding up a bunch of stuff, the degree of the whole thing is the degree of the highest component. So, you know, if you're adding x squared and x squared is quadratic, that's going to be x being linear. You're taking the max. Okay. So that's B max, degree Q, degree R. And any suggestions for how we should compute the degree of a formula that's a product? Like if the degree, so the degree of x squared is 2 and the degree of x is 1, what's the degree of x times x squared? 3. What are we doing to the degrees? We're adding them. Okay, so we've got a candidate definition of degree, and it's about as far from an accident as you could possibly want. So what's going on here? We remember that the type formula has numerical constants, including, so 0 and 1 are both numerical constants, and it's got syntax for adding, and it's got syntax for multiplying. That is to say, the type formula is a syntax for calculations in a rig. We've got a plus for the untermonoid and a times for the ubermonoid, and we've got the neutral elements of addition and multiplication. And there's basically, once you know what the rig is, and once you know what to do with the variable, you're basically sorted. So what's happening here is that we are interpreting the same notion of formula, but not in your usual rig. We're interpreting the formula as a calculation in the Botnum rig that you built last week. But we're still sending the Ubermonoid to the Ubermonoid, the Untermonoid to the Untermonoid. And that's the other reason why we're sending 0, which is the neutral element for the Untermonoid, to bot, which is the neutral element for Bmax. The only real choice was to decide what to do with the variable, and that we sent to 1. Okay. So that's kind of nice. That, you know, it wasn't a big accident. That was, you know, if you recognize which role is being played by which operator, then all the rig components match up between the syntactic formulae and the botnum rig. And that's what we've got here. And in fact, it is annoyingly nearly but not quite the case that degree is a monoid map from substitution to multiplication. Certainly works some of the time. Sadly, there are awkward corner cases at around 0. But certainly you can imagine that if you've got like a formula x cubed and you substitute x squared for x, then that's x squared all cubed, which is x to the 6. So for the most part, substituting formulae multiplies their degree, apart from a few edge cases, which is why we're not going to try and prove it, because it isn't true. However, at least instinctively, you should imagine that if you shift a formula, if you replace x by 1 plus x, that's not going to make any difference, right? All you're tweaking, you're just moving the x-axis around. You're not changing the shape of the graph. Or is it the y-axis you're moving around? You're shifting things sideways. You're shifting the graph sideways. Okay, so we are going to need the fact that the degree of shift p is equal to the degree of p. So we had better prove it. So this is me giving you a freebie as far as your homework is concerned. And also making sure I've got enough content for this lecture. So we ain't got much choice here. If we can't, I mean, I'd love to be able to do it by just saying, oh, look, x plus 1 is degree 1, but doesn't work out. So I'm just going to do it brute force and ignorantly with inductively. Right. And you'll see that that works out okay, except we get terrible names, which I'm going to change because I've got time. And we know we're going to go do inductively and then from and then test, because that's just life. And then it gives us an ugly expansion of shift again. Right. Uh, okay, so that's our goal. Um, any suggestions for what we're going to do? What move would you make? Let me give you a clue. Any suggestions? What do we know inductively? It's uh, we want to use the induction hypothesis somehow. Um, we could do a by route that replaced these degree. Oh, I'm missing a parenthesis, a bracket here. Um, um, we could do a by route replacing left-hand side by right-hand side with induction hypothesis, but that's overkill. Do you see these B maxes just line up nicely? So yeah, we can just go under B max. And that's that one done. And okay, I will line this one up as well. Uh, under is a way of explaining that an equation that has the same function on both sides is true because you get the same outputs when you supply the same inputs. So what I'm saying is, what I'm saying is, you see, I've got B max on the left, I've got B max on the right. I'm saying I want to prove this equation is true because the first input to B max is equal to, on the left, is equal to the first input on the right. The second input on the left is equal to the second input on the right. I'm saying I want to, so the explanation is equal outputs because equal inputs. And in this case, both of those equations that I now need to prove are given inductively, so we're done. Right? So under's not a big, it's not always the case that you get equal outputs because you have equal inputs. So for example, I mean, as I'm fond of saying, well, that, you know, you can't prove that 3 plus 7 equals 5 plus 5 by proving that 3 equals 5 and 7 equals 5. That ain't gonna work. But here, they line up perfectly. And very often it's the case that we need to use associativity to line things up ready for under, just to get the right pieces matching up. Okay, so I'm gonna hit send here. You're going to get a monstrous sense of deja vu, I suspect. Because our next move is, of course, to say test. And then ask will do a whole pile of this thing is shift Q. And this thing here is shift R. And what do you think we should do, folks? Again, not by accident, these triple pluses just line up. So we are in a position to make the explanation. Same output because same inputs. Okay, so that's that done. We've got a useful piece of equipment, and you get this already given to you for the homework. So I'll just finish by surfing quickly into the homework. So it's two parts to the problem. One is to cook up, but the clue I'm going to give you is to do the homework backwards. Right. So here I'm asking you to define bpred, and I'm telling you that the obvious easy cases of bpred are when there's a one to take away. So if we start with a number that is bigger than 0, we subtract 1 from the number, right? That's my shut up alarm. If on the other hand, if we get a number which is 0, or we get minus infinity, you will have to think about what predecessors should do to them. And it might not be obvious straight away. But the crucial thing is, you don't have to make your mind up straight away. Instead, you can start trying to do this proof. And when you do, this proof will force you to make the right choices for the edge cases of bpred. The other thing, of course, you can expect is that since degree uses Bmax and triple plus all over the place, you are going to need to prove some useful things that relate bpred with the rig operations, because you will need some algebra for that. And I'm not going to tell you what to prove. Your attempt to do this proof will show you what extra equipment you need to build for yourself. So I'm asking you to use your initiative and figure out what algebraic facts might help. Okay, I think that I should probably call it there, and wish you an excellent week 6. I shall say cheerio to YouTube.